So this is Advanced Thermodynamics and Combustion being conducted by IIT Guwahati under the NPTEL program. And this is the seventh live tutorial session of this course. And the theme of today's session is properties of gas mixture. Basically, this is the continuation of the previous session's theme. And the instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I'm the teaching assistant for these tutorial sessions, and my name is Aditya Sharma. Also, I'm a research scholar from uh, Department of Mechanical Engineering of IIT Guwahati. So we shall be starting in another couple of minutes. So let's see if somebody joins. Otherwise, we shall start the session. Today's session. Okay, so we can start with the today's session. So the theme is properties of gas mixture, and the session has been divided into three sections. In the first section, we briefly discuss the topics that have been covered in the week 7 of this particular course. In the next section, we deal with conceptual questions. And the last section, the third section, is on numerical questions. where we try to solve few numerical problems. So this way we shall proceed for this tutorial session. We have been doing this in the previous session also. Let's see. So two lectures are there in this particular week, that is week 7 of advanced thermodynamics and combustion. In the previous week, we were introduced to different gas models, right? So there were two types of models. One was ideal gas model, and then second one was real gas. So we are very much familiar with the ideal gas model, that is PV equals to nRT. Then there were real gas models, like van der Waals model, and then the second real gas model was Redlich-Kwong model. So these two models we came across in the previous week's discussion. Also, as the name suggests, the theme is property of gas mixture. So we basically are focused with the properties of the gas mixture which is in our hand. So in that line, in the last week's discussion, we saw discussion on properties like chemical potential, property like fugacity. Okay. Yes. And then we also saw the partial molar properties, the properties pertaining to different components of a mixture when they are uh, in the mixture state in some mixture. So this is about the discussion of the previous week. Now continuing with that discussion, in this week's content, the first lecture is lecture number 17, and the first topic in that is ideal gas mixture. So in ideal gas mixture, what we saw is that we have some mixture composed of two or more components or two or more gases, and they behave ideally, right? The whole idea of doing the study of mixtures is that it is used first in psychrometrics, right? And also we come across the mixtures in combustion studies. So these are the two applications that have been discussed under this topic. So from that perspective, we do this study of mixtures. Okay. So this was ideal gas mixture. And then second topic in this lecture was mixture composition. So this is a very fundamental topic as far as the discussion of mixtures is concerned. Because here we define the composition of a mixture in terms of different terminologies. Okay, so be it mole fraction, be it volume fraction, be it mass fraction, all these terms have been introduced under this topic. Okay. So in mixture composition, if we have to get the total mass, that is very straightforward. We will add the different masses of different components, and this is how we get the total mass. Then there is total number of moles. That also is very straightforward. We can add the total number of moles of each component, and this is how we can get the total number of moles. Right? Then comes mass fraction. Mass fraction basically is the mass of component in a particular mixture over total mass. Okay, in mixture. So this is your mass fraction. The same way is the mole fraction. Before mole fraction, I believe I should write what is mole. Though very basic. So this is your weight over molecular. So the weight of a particular matter or gas in hand to the molecular weight of that uh, gas. So this is your mole. Okay. Then mole fraction is number of moles of a component in a mixture divided by total number of moles. Okay. So this is your mole fraction. Then third is your molecular weight of mixture. So this is interesting parameter. So how do we calculate the molecular weight of a mixture? So what do we do? We write the total weight of a mixture and then we divide it by the total number of moles. So this is how we get the molecular weight of the mixture. Yes, if you hear some noise in the background, it's raining here. So please bear with that in case there is some noise. Okay, so we can understand it with uh, The example of air maybe. So if you see example of air, it has nitrogen, oxygen, then argon, then CO2. Okay. The percentage in which these are found is this. So we find the molecular weight. Total mass divided by total moles. And please remember that air in this case acts as a mixture. Okay. So if we write this M, it can also be written as this. Where I is the component number and J is the total number of components that are there in this mixture. Okay. Mi is the molecular weight of the component I in the mixture and yi is the mole fraction. So in this way it becomes, because 28 is the molecular weight of nitrogen, 32 is the molecular weight of oxygen, 40 is the molecular weight of argon. Maybe I should write 39.9 only. And then 44 is the molecular weight of carbon dioxide. So if we work this out, this comes out to be this. So this is your molecular weight for air as a mixture. So this was your discussion on mixture composition. And then next topic is PVT relations for a mixture. So first heading, as I have told, is ideal gas mixture. So here we are discussing the ideal gas mixture. So in that case, if a mixture is considered as a single entity, so we can use the ideal gas equation in that case and work out the different properties of a mixture in whole. Okay, so that can be done using the ideal gas equation for a mixture. That is possible. Okay, so there are two suppositions for a mixture to be ideal. The first one is that the forces between the molecules of the mixture are negligible. In the discussion on real gas models, we saw that the forces between the molecules of real gases are not negligible. But because here we are concerned with the ideal gas mixtures, so in that case, this has to be negligible. Other than that, the volume occupied by the molecules in comparison to the volume occupied by the whole gas is pretty small. Or for that matter, we can take this to be, for the matter of our discussion, we can take this to be negligible in case it's an ideal gas mixture. So this way, with these suppositions, we can use the ideal gas equation for our mixtures. Okay. And in this topic, later we were introduced to the partial pressure concept. So if there are n number of components in a mixture, the pressure exerted by some particular component I. Okay. So how do we calculate that? Right. So this we see in this topic. So that basically is related to the total pressure first of the mixture and then the mole fraction of that component in the mixture. These two things govern the partial pressure of the component. Okay. So let's say we have n number of moles, okay, in a mixture, and P is the pressure of the mixture, and V is the volume of the mixture, and T is the temperature. Right. So in that case, your pressure becomes nRT by V. So this becomes your pressure. Now, if you want to calculate the partial pressure of some component I, let's say we have component I. In that case, its partial pressure can be written as number of moles, because the volume remains same for the component in a particular mixture. The difference is from the whole mixture is of the number of moles that a particular component has in a particular mixture. Okay. And if you take the ratios of these two, what do we find out? That if you take this, so this is your mole fraction, right? So similarly for volume also, so this is your partial pressure, Pi. So from here you can have Pi equals to Yi by Yi. So this is your partial pressure in terms of its the component's mole fraction and the total pressure of the mixture. Then there is your volume fraction. Same way, volume fraction can be reduced. the expression for it can be found out. So this was your discussion on PBT regulation. And in the last, thermodynamic properties of a mixture. So here we saw different properties in relation to a mixture. Properties like internal energy, properties like enthalpy, properties like entropy, and then specific heat. So if we have a mixture in our hand, in that case, if we have to calculate all these properties, then how do we do that? And if we have, for example, internal energy of different components, then how do we find internal energy for the whole mixture? If we have enthalpy for different components, how do we find for the whole mixture? If we have entropy for the different components of the mixture, how do we find for the whole mixture? So these all these formulae we saw in this particular topic. So the calculation is straightforward. For your uh, internal energy calculation, for your enthalpy calculation, for your entropy calculation, we can directly add the different components, the contribution of different components in a mixture, and by adding these, we can directly get the final property of the whole mixture. Okay. If you want to calculate the internal energy of the whole mixture, so internal energy for all the components, we can add them up and get the internal energy for the mixture. Same way we can do for enthalpy, entropy, right? And then there is a formula for specific heat calculation also. So all this can be worked out. Okay. So this was your lecture 17. Now coming to lecture number 18. So in this lecture, some amount of rigor you will get to see, you must have seen, in terms of different expressions that have been worked out under different headings. So let's see this one by one. So first is your mechanism of mixture formation. So how do a mixture forms, and when a mixture forms, what are the changes that we see in the components in comparison to uh, the way in which different components are in the mixture. Okay. So in their pure form, how the components are, and when they are part of a mixture, in that case, what is their state? So this has been discussed in this topic. So one important point to remember is that when mixing takes place, it's an irreversible process. Okay? and because it's irreversible, there is entropy production in that case. So entropy production we saw in the discussions of week 2 and week 3 these lectures. Okay, so there we saw that how irreversibility contributes to entropy production. In the entropy balance also for a closed system and for a controlled volume, this entropy production was there in the picture. So if you revise the content of week 2 and week 3, you will be able to understand on the. Okay. So this topic states that there will be entropy production and what are the factors that contribute to this entropy production. So three such factors have been enumerated. So first is that from the initial stage, the temperature differences are there in the components. This is first. And then second is that there are pressure differences. Okay. Then third, it states that gases are distinguishable from one another. So these three factors have been discussed in this particular heading. The main thing you have to remember is the entropy production. Then second topic is mixture processes at constant composition. So in this case, what we do is we have a mixture in which the composition of this mixture in terms of the different components it has, that remains same. Okay. So for such cases, how do we calculate the internal energy changes, enthalpy changes, and the entropy changes? So this has been expressions for this has been given under this heading. So basically, for the internal energy and enthalpy changes, the two states considered, the initial and final states, in that the temperature that these states hold plays an important role in getting these the change of these properties, okay, of internal energy and enthalpy. Same is also the case for your entropy, but in this case we consider pressure also in addition to the temperature of the state. Right? So the expressions have been given and are a bit time consuming, so I won't write these expressions for this session. Okay. You can refer to the slides of this week's content for the expressions. Then this next topic is compression of an ideal gas, and after that is expansion of the ideal gas. So again, we are discussing ideal gas mixture. So in that case, if we have to compress a mixture, or if we have to expand a mixture, we have to compress a mixture by means of a piston, or if your mixture is expanding by means of a nozzle. In that case, how the properties change and how we deal with those property changes. So this has all these expressions have been mentioned in this topic. So for the compression, we consider the process to be a polytropic process. Okay, that is polytropic processes. So if your mixture behaves is governed by this expression, in that case, it's a process of the mixture is governed by this expression, then it's a polytropic process. Okay? Then expressions for work transfer is also there in this topic, right? And then expression for internal energy change has also been mentioned at this particular topic. Then is your same is the case for your expansion process. Okay. So here the entropy change expression has been given, and then energy rate balance. So if there is expansion by means of a nozzle, so if we consider the flow to be steady, in that case the energy rate balance, how do we write that? So this has been given in this topic's discussion. Okay. So this was about your compression and expansion of ideal gas mixture. Then next topic is your on mixing. So for mixing condition that has been kept is first of all adiabatic. Then there are two cases that have been discussed. So this is your first is your adiabatic mixing at constant total volume. Then is your adiabatic mixing of two streams. Okay, so first is your adiabatic mixing at constant volume. So in this case, the mixing of two gases that takes place. First of all, it is an ideal gas mixture. Okay, and then the mixing that takes place is adiabatic. That is, there is no heat transfer across this mixture. Okay, so in that case, if we see our energy balance, so I'll just briefly. So in your energy balance, this is the first thing that your internal energy change is zero. Okay. So expression for it has been given in terms of your specific internal energy for gas 1, for gas 2, at temperature, initial temperature, and then specific internal energy at the temperature of mixture that is T2. Okay. So These two things have been given. Then also the expression for final temperature has been calculated by means of this expression, internal energy expression. Okay. Then there is expression for your final pressure also. And at last, the discussion is on the entropy balance for a closed system. Okay. So entropy balance S2 minus S1 equals to. So you must be remembering that this Q is for your heat transfer across the boundaries, right? And then your this is your entropy production sign, which is because of internal irreversibilities. And then a expression for this entropy production has been given for this adiabatic mixing at constant total volume. Then second is your adiabatic mixing of two streams. So in that case, we will have the control volume approach for our entropy balance. So we saw in the our entropy balance discussion in week 2 and week 3. This I was discussing earlier also that there were two cases. One was your closed system and then another was your control volume case. So the topic of your constant adiabatic mixing and at constant total volume. In this case, if we have to have the discussion on entropy balance. So in this case, we use the entropy balance for a core system. Sorry. And in case we have to have the discussion of entropy production, in case our entropy balance for the adiabatic mixing of two streams, in that case we will have the entropy balance, balance for a control volume. Okay. And if we consider that the flow is steady, in that case the things become a bit easy in terms of getting your expression for the entropy balance. Okay. So all this has been discussed in this topic. So now we will move on to the questions. This was your discussion on the topics that have been covered in this week's content. Okay, so let's move on to the questions. So this is your first question. So let's try to answer this question. The numerical questions are more in this week's session, tutorial session. But we have uh, had some amount of these theoretical questions also. Okay. First question. So the question is on mixture composition, and it says that the sum of mass fraction of all the components in the mixture is 0. So whether this is a true statement or false statement, because the question asks about mass fraction, so this is your mass fraction, this is your mass of a particular component in the mixture to the total mass of the mixture. So in any case, if there is some component, it will have some mass, and the mass fraction of it will always be greater than 1. Okay? Sorry, greater than 0. Not 1, but greater than 0. Sorry. Okay. So if the statement, when the statement says that the sum of mass fraction of the all components is 0, in starting only this proves to be a false statement. Okay. Other than that, if you take the sum of all the mass fractions of different components, you will find out that the sum for all the mass fractions comes out to be 1. Okay. So 1 is for the whole mass of the mixture, and then out of that, different components have different shares in terms of mass that we call as mass fraction. So answer to this question is B. Now moving on to next question. You can try to answer this question. The question again is based on mixture composition. Okay. So this is your second question based on mixture composition. And the question says that question asks that which of the following terminologies used for the listing of mass fraction of components of a mixture. So in our analysis of a mixture, when we obtain the different mass fractions of all the components of a mixture, in that case, such analysis is called what? And whether that term is there in the given options. So if you see your first option, that is molar analysis. So molar analysis basically is when we discuss the mole fractions of different components and the number of moles of different components. Okay, so that is your molar analysis. Then is your volumetric analysis. So molar analysis is sometimes known as volumetric analysis also. So these are one and the same things as per your slides. But also we have seen that for your volume fractions also, we see that mole fractions prove to be handy. When we define in terms the mole fraction of a particular component of a mixture in terms of the total volume of the mixture and the mole fraction of that particular component. So fractions, mole fraction proves to be very useful. Then your third is gravimetric analysis. So this is your correct option. So when we enlist different mass fractions of the components of a mixture, to such analysis we give the name gravimetric analysis. Okay. This is the correct option. So moving on to next question. The topic is PBT relations for a mixture. This is from your lecture 17. Lecture 17's heading, one of the headings. So please, question number 3, we can try to answer this. So the question says that this is question number three. Ideal and real gases are composed of molecules that exert negligible forces on one another. We will stop here. So if you remember the discussion of previous week, I believe it's lecture number 15, if I'm not wrong. So there we discussed real gases and real gas models. And we saw there that it has been explicitly mentioned in the content of or in that discussion that real gases, the molecules of real gases exert force on each other, and because of this force, the pressure that is experienced on the walls is less in comparison if we take the same gas in ideal conditions. If we consider the same gas as ideal, okay, that is the difference between an ideal gas and a real gas. So if your expression says that question says that ideal and real gases are composed of molecules that exert negligible forces on one another, in that case it's a false statement because real molecules of real gases do exert considerable forces on each other, and because of that only we have different models to define the real gases. Okay, so this is a false statement. So next is your fourth question. And before moving on to the fourth question and further discussion, we shall have a 5 minutes break because it's almost 4 o'clock, 1 hour past the starting of the session. So we shall meet in another 5 minutes. Thank you. Okay, so we can start with the continue. Sorry, with the session, remaining session. So we have another 1 hour or 55 minutes of the session. So the next question is question number four. Question number four is on the topic mixture composition, and it says that the apparent molecular weight of the mixture is defined as the ratio of. Sorry. So this question, I believe we will not consider for this session because it's not in proper form. So let's skip this and move on to the next question. Okay, so we have next question. Basically, this question was on your apparent molecular weight, where I had to give the fill in the blanks, but then I somehow didn't give the fill in the blank. Didn't. So here these needed to be as fill in the blanks, and then this question would have been considered, but because I forgot to do that, so apologies for that. So we'll skip this question and we'll move on to the next question. Okay. So next question then is on your pressure, volume, temperature relations for a mixture. So this says that your additive pressure rule is a special case of Dalton model. So you can try to answer this. So your additive rule basically is the rule which says that for a mixture, we have to get the total pressure. In that case, the sum of the pressures of different components of that mixture at a value of temperature and volume which is same as that of mixture. If we do the sum of such pressures of different components of all components of the mixture, in that case This is your additive pressure rule, and we can get the total pressure of the mixture. And what is your Dalton model? Dalton model we saw in our discussions on ideal gas mixture, right? Where we saw that the different partial pressures related to the components of mixture. When we add those partial pressures, we get the total pressure of the mixture. This pressure, partial pressure, we define on the basis of total pressure of the mixture and then the mole fraction of the component for which we are trying to find the partial pressure. And the addition of different partial pressures of all the components of a mixture lead to the total pressure of the mixture. Okay. So now we can try to answer this, whether the statement is correct or not. So the thing here is that your additive pressure rule is a general rule. Okay, and your Dalton model is for your ideal gas mixtures only. Okay, so Dalton model has to be a special case for the additive pressure rule and not vice versa. Okay, so when the statement says that your additive pressure rule is a special case of Dalton model, in that case, this becomes a wrong statement. So it had to be this way. So in that case, this becomes a false statement. Okay. So moving on to the next question. This is your question number 6, and the question is on mechanism of mixture for formation. You can try to answer this. Okay, so the question says that which of the following factors does not contribute to entropy production in the mixing of gases? So four options we have. First option is your reversibility. Second option is your irreversibility. Third option is your difference in the temperature before and after the mixing of the gases. Difference in the pressure before and after the mixing of the gases. So when there is mixing of gases and we get a gas mixture, in that case there is entropy production. So which of the following is not a valid reason for the entropy production in case of mixing of gases? So we have discussed that entropy production is because of irreversibility only. Right? So the internal irreversibilities in the system lead to entropy production. Difference in temperatures does lead to entropy production. Difference in pressures is one of the factors that has also given in the uh, has also been discussed in the lectures. So in that case, your A option is the one. Which is not a correct explanation for entropy production in case of mixing of gases. Okay, so A is the correct option. So moving on to next question. The topic of the question is thermodynamic properties of a mixture from lecture 17. This is question number 7. You can try to answer this question. Just give me a second. Okay, so this is your question number 7, thermodynamic properties of a mixture, and it says that the enthalpy H of an ideal gas mixture can be found by adding the contribution of each component at the condition in which it exists in the mixture. So whether this statement is correct or not, so we know that enthalpy is also one of the properties that can be calculated by directly adding the enthalpies of different components of a mixture and then coming out to get a total enthalpy of the mixture, right? So this is the case for entropy also. This is the case for internal energy also. Okay. So so in that case, this is a correct statement. Okay. So if you see this, Answer to this question is A. All right. Now moving on to next question. The question is on mixture composition, and it's a factual question. It says that what is the molecular weight of air in kg per kilomole? Yes. So I have done this. I have worked this out here. So if you see the molecular weight of air and how we came to this molecular weight, that also I have discussed. So the value here is 28.97. Okay. So if you see your four options, out of all these four options, your option C is the correct one. Right? Okay, so moving on to next question. So this is on adiabatic mixing at constant volume. So this topic is from your lecture number 18, the second last topic of lecture number 18. And the question is a true or false type of question, and it states that the internal energy change in case of adiabatic mixing of gases at constant volume is finite. So in the discussion of adiabatic mixing at constant volume, we also saw that in adiabatic mixing at constant total volume, the internal energy change from initial to final state, this remains constant. Or, sorry, the internal energy change is zero, right? That is the internal energy remains same. So if it says that the change is finite, in that case this becomes a false statement, right? In that case, this becomes a false statement. Again, it says that It is finite, but it has to be 0. So moving on to the next question, which is on adiabatic mixing at constant volume again. It's the same question. So this is on previous was asking about your internal energy, and this one is asking about entropy production. So the question here says that the entropy production in case of adiabatic mixing of gases at constant volume is finite. So whether the entropy production is finite or not in case of adiabatic mixing. So we have seen that in case of mixing, there are irreversibilities that are there because of this mixing, and the factors that contribute to that irreversibilities has also been mentioned previously. So in that case, if there is mixing, then there will be entropy production. And if the statement says that the entropy production is finite, in that case this becomes a true statement. Okay. Now moving on to, so this is A option is correct. Sorry. Moving on to your next section, that is numerical questions. So let's see how many numerical questions we are able to perform. I have total 7 numerical questions in these slides. So I hope we are able to cover all those. So this is your first numerical question. It talks about a balloon whose diameter has been given and the atmosphere in which it floats has also been given. And now it asks for the amount of moles that have been displaced by this balloon. So we have kept this balloon as spherical. Okay. So let's try this out. So how can we calculate the number of moles? We have balloon, we will consider that balloon is spherical. For moles, we need the mass of air that is there in the balloon, and then we need the molecular weight of air that we have. So how we will calculate mass? So we will use the PV equals to RT expression. PV equals to MRT, right? So this is your question number 11 solution. Molecular weight of air is 28.97 kg per kilomole. So now volume of, so your mass of air displaced is PV by RT. Okay, sorry. Here we have pressure, we have R, we have temperature, but we don't have volume. Okay, so we'll calculate the volume of balloon. This is it. Because diameter is 10, so radius will be 5. And if we work this out, this comes out to be 523.59 meter cube. So mass of air displaced is, pressure is 102 kilopascal. R is 287 into temperature is 288. So this comes out to be 646.138. Okay, kg. So moles of air displaced. Now is total weight divided by this. So this is our answer to question number 11. Now moving on to question number 12. So topic here is entropy of a mixture. Previous topic was mixture composition. This is that 4 kg of oxygen at some degrees mixed with 8 kg of nitrogen at the same temperature. Initial pressure has been given. Okay. The pressure doesn't change. It remains same for the mixture and for the components also, for the constituents. Now we need to find the increase in entropy of mixture. Universal gas constant, we need to take this. Okay. So entropy change can be found out by this. Expression. Okay, now what do we need to find out? Mass of oxygen, that is MO2, we have. Mass of nitrogen, we have. Right. Now, gas constant for oxygen and for nitrogen on the basis of their molecular weights, individual molecular weights that we can work out, that we need to work out. And then partial pressures, the ratio of partial pressure to that of total pressure, we need to find out. So we know that your mole fraction is equal to this, right? So this is basically n of O2 by n of O2 plus n of N2. So this can be written as this. So plus 8 is the weight of nitrogen that is there in the question. So if we work this out, this comes out to be 0.304. If there is some mistake in the calculation, you can intimate me in the comment box. Okay. And then for nitrogen, the same way, but we can also do it this way because the total number of, if we add sorry, all the mole fractions, that comes out to be 1. In that case, for nitrogen it comes out to be 0.696. Okay, now placing the values in the entropy change expression. So entropy change equals to minus 4, 8.314 divided by 32 ln 0.304 minus 8.314 divided by 28 ln 0.696. Okay, so if you calculate these, this will come out to be this. So this is your entropy change. Okay, now moving on to the next numerical. So there are 4 set of numericals based on this information. So this is 1.2 grams of helium has been given and 1.2 grams of nitrogen has been given. So they are mixed in a chamber at this and this temperature and pressure respectively. So only this much information is given. So first question asks for calculation of the mole fraction of helium. So let's calculate the mole fraction of helium. First we'll calculate the number of moles. So number of moles for helium is 1.2 divided by 4 is the molecular weight of helium. So this comes out to be 0.3 kilomoles. Okay. And this is the number of moles for nitrogen. So mole fraction for helium comes out to be 0.3 divided by 0.3 plus 0.0428. And this comes out to be this. So this is your solution number 13. Now for 14, calculate the volume fraction of nitrogen. Sorry, I displayed the answer by mistake. That's okay. Calculate the volume fraction of nitrogen. So let's calculate the volume fraction. So volume fraction can also be calculated directly from the mole fraction, right? So this we have learned. So volume fraction of nitrogen equals to NG. That is Y of N. Y of Nt is also 1 minus Y of O2 because only two components are there. And the sum of mole fractions of all the components is 1. So 1 minus from the, sorry, this is not oxygen but this is helium. Helium and nitrogen are there. Okay, so this is 0.8751 and this comes out to be 0.1249. Okay, so this is your mole fraction, volume fraction for nitrogen. That is why it is sometimes known as volumetric analysis. Molar analysis is also known as volumetric analysis because volume fraction also you can calculate. Okay, so this was question number 14. Okay, now moving on to next question. So this is on thermodynamic properties of a mixture, and it says calculate the specific heat at constant pressure, that is Cp of the gas mixture. So we need to find out the Cp. So how do we do that? This is your question number 15 solution. So first we will calculate the individual specific heats for both helium and nitrogen, and then based on the mass fraction of helium and nitrogen, we will calculate the total Cp. Right? So Cp of gas mixture basically is helium divided by mass of helium okay. Now if you calculate the Cp of helium, that is gamma by gamma minus 1 into R. But now R here has to be of helium only. So also because helium is monoatomic gas, so gamma in its case will be 1.67. More is the molecular weight of helium. So if we calculate this, this comes out to be this. And for nitrogen, if we calculate, because it is diatomic gas, in that case gamma will be 1.4. So if we work this out, this comes out to be this. So Cp of gas mixture is 1.2 into 5.1809 plus 1.2 into 1.0393 this. And now if we work this out, this comes out to be this. So this is your question number 15. Now let's see question number 16. The topic is thermodynamic properties of a mixture. Question is calculate the gas constant of the mixture. So this is the last question based on the information that was given. So gas constant can also be calculated this way. So this is your mass of helium, then gas constant of helium plus mass of nitrogen, and then nitrogen divided by mass of helium plus mass of nitrogen. So this comes out to be 1.24. If you work this out, this will come out to be 1.1877 kilojoule per kg Kelvin. Okay. So this was your question number 16. So we are almost done with today's session, but I have one extra question. So based on your ideal gas equation, we have to find out the pressure here. Moles have been given for methane and butane, and volume and temperatures are given. Okay. So based on ideal gas equation, let's see what do we get. Right. So ideal gas equation we have PV equals to RT. Right. Now, but we have volume and we don't have V bar. Right. So for methane and butane, right, two gases we have. One is 0.14 and other is 0.223. So total number of moles will be 0.2. So this will come out to be, this is your V bar. So pressure will come out to be 8314 into temperature is 221 degrees Celsius, which is 221 plus 273 in kelvins divided by 0.606 is your V bar, right? But now if we want this in bars, right? So what we can do, we can multiply the whole thing by 10 to the power 5. So if we solve this, this comes out to be 67.77 bar. So this was your last question of today's session. So I'll conclude then the session. So this session was on properties of gas mixture. So in the previous session of properties of gas mixture, we saw the ideal gas model, real gas models, and then properties like chemical potential, fugacity, and then also ideal solution we saw in the previous week's content, and then partial molar properties were also discussed in the previous week. And then in this week, we continued with the this properties of gas mixture, where in starting of this week's content, in lecture 17, we saw topics like mixture composition. So all the discussions were with respect to ideal gas mixture, right? So we saw topics like mixture composition, right? And then to solve for the pressure, volume, or temperature of a mixture, we saw that we can use the ideal gas equation for that. Okay. And then later we saw how to calculate the thermodynamic properties vis-a-vis a mixture, ideal mixture. Properties like internal energy, enthalpy, and then entropy. So all this was discussed. Then in the next lecture, we saw that if we compress a mixture or if a mixture expands, in that case, how the properties change and how we can calculate those properties. And then we saw two special cases in adiabatic conditions. One was at constant total volume and one was of mixing of two streams. The former one, the entropy discussion on the entropy balance in the former case was done by considering it a closed system, and for the latter one, the discussion, the entropy balance discussion was keeping in mind that the system is a control volume type, right? So the entropy balance has been discussed by considering a control volume in our whole scenario. So these were the topics that were discussed in this week's lecture. And after that, we saw conceptual questions based on these topics. In total, 10 conceptual questions were discussed. Okay, and after that, we saw few numerical questions based on mixture composition, pressure calculation, and then specific heat calculation of the mixture, mole fraction calculation, volume fraction calculation. So all these numericals we worked out in the last section of this session. So in this way, we conducted our session, and I thank you for joining this session. And you can watch these sessions on the YouTube links that will be provided to you all. So we shall meet again in the next session in the coming Sunday with the same timing, that is 3 to 5 p.m. And till then, keep learning. Happy learning and goodbye. Thank you.